Well, welcome. Good afternoon, everyone, and welcome to the very first webinar of our Bite-Sized Corrosion series. For those of you who don't know me, my name is Vanessa Seeley-Fisher, and I'm a director at Isiniti. Today is our first webinar in a 6-week series of free weekly lunchtime corrosion conversations. An opportunity to introduce you to the very basic concepts related to corrosion and cathodic protection. And we're very excited to be partnering with Isifundi Training today to bring you this discussion on cathodic protection. We hope that today's corrosion conversation will be valuable to you. We'll introduce you to some concepts that perhaps you haven't really grasped beforehand. It's going to be fairly high level, introductory for largely the engineers among us. But really just some introductory comments that hopefully whet your appetite until you too find a passion and a love for this thing called corrosion that I've enjoyed. Right now, I'd like to introduce our speaker for today, Mr. Neil Webb. Now, I know many of you know Neil, but for those who don't, Neil has a wealth of experience and numerous qualifications in engineering and cathodic protection. As a chartered metallurgical engineer, a chartered scientist, and with over 40 years experience in CP design, stray current mitigation, and latterly AC mitigation, he's well placed to lead this discussion and answer our questions. Neil has been responsible for several innovative cathodic protection systems for pipeline networks and for tanks in both conventional and hazardous environments. So sit back, grab your lunch, and let's listen to what Neil has to say. Neil, over to you.
Thank you, Vanessa, and hello to all of you out there who are distributed across the world, some 15 time zones and both of the hemispheres. As I was preparing for this discussion, I was struck by the thought that corrosion, like COVID-19, would be a worldwide pandemic if we couldn't control it. Some years ago, I presented a talk entitled Cathodic Protection, Medical Aid for Pipelines. So I thought it would be fitting to use this medical terminology as an illustration of the application of cathodic protection. Just as human anatomy hasn't changed over the last 35 years, neither has corrosion. Like medicine, our understanding has improved, as has our treatment of new challenges that have arisen. Many people consider cathodic protection to be some mysterious art or witchcraft, but actually it's based on well-established laws of physics and chemistry developed by Ohm, Kirchhoff, and Faraday many years ago. Now, just as a doctor has to understand anatomy if he is going to treat human illness, so we need to understand the basic electrochemical equation that takes place in the metal that we are dealing with. Any conductive metal comprises a matrix of metallic ions which are surrounded by a sea of electrons. When electrical current flows, these electrons move. As long as the current flows inside the steel or the copper or whichever conductor it is that we're talking about, then there is no damage done to that steel. However, if the current enters or leaves the steel surface from a solution such as seawater or fresh water or soil, then we get reactions that take place between the steel surface and the environment. There are two reactions that take place. Where current leaves the circuit, you get what we call the anode. And at the anode, the metal leaves the steel surface as metallic ions, and corrosion occurs. Somewhere else on that same surface, the electrons that are released by that circuit, by that reaction, have to react with the environment, and we get the cathode. And at the cathode, we produce hydrogen or consume oxygen to form hydroxides. Now, you may say, well, that's all very well, but on a steel pipeline, which is what we're going to consider primarily in this discussion today, we only have a single surface. The problem is that even though we have a single surface, the interaction between that surface and the electrolyte will change depending on the conditions. And so some areas of the surface will be cathodes, others will be anodes, and the underlying substrate forms the electric circuit. As long as those two surfaces are both in the same electrolyte, corrosion will occur at the anodic surface. So what are the symptoms of this illness that we call corrosion? Well, one of the symptoms of a corrosion of a pipeline is a leak. And unfortunately, we see these unintended leaks from time to time in the form of fountains where there shouldn't be, especially when they're in the middle of our busy streets. And what causes these illnesses? Well, just like there's a variety of microbes and viruses around that cause physical illness, just so we have different types of corrosion that can occur on buried pipelines. Firstly, believe it or not, and this is not necessarily in order of importance, we have the situation where pipelines corrode as a result of actual bacteria. Now, these bacteria don't literally eat the pipeline or the steel, but they exist under conditions where the byproducts of the bacteria cause very corrosive conditions to develop, and we can get quite severe corrosion of the underlying steel. This particular example was a situation which was considered completely non-corrosive, except that nobody bothered to test for the presence of bacteria, and perforation of the pipeline was the result. Perhaps one of the more common types of corrosion that we get with pipelines is what one could call general corrosion. Although most pipelines actually corrode by pitting rather than overall general corrosion, perhaps soil corrosion would be a better term to use. General corrosion occurs over the entire surface and is related to the characteristics of the soil. And although for many years we've tended to look at corrosion as being related strictly to resistivity of the soil, we are finding these days that even in high resistivity soils, that we still get actual corrosion occurring. When we get different soils, we then get what we call a long cell. So here we have a situation where there are pipelines which traverse from the position of the photographer across that loch. This picture actually comes from Scotland, through the dunes and into the sea. So you can see that we have 4 different environments in that situation. And depending on the characteristics of those environments, we can get certain areas of the pipeline being anodic, others being cathodic, and corrosion of the pipeline occurs in the anodic areas. Chemical attack, fortunately, is fairly rare. It can be pretty severe when we have chemical contamination of ground conditions. And sometimes these are unavoidable. We have, for example, in South Africa, we have situations where pipelines are installed close to mining activities, and you land up with the runoff from some of these mine dumps. Although it is contained from an environmental point of view, we can land up with fairly localized, aggressive situations. One of the contributors to our illnesses is that of electrical interference. This really blows the mind of a lot of people. But actually, because corrosion is an electrochemical process, electrical interference actually has the same effect as a corrosion cell, in that we get current entering and or leaving the pipeline. This current can be produced by interaction with overhead high voltage AC power lines, or more often it is associated with DC traction. In South Africa, again, we have a fairly aggressive situation because we have fairly high-powered DC rail systems. And as we see this train moving past, you can see that there are 4 locos up front, which are drawing several thousand amps. If some of that current gets into the pipeline and then discharges on its way back to the traction substation, we can get catastrophic corrosion of the pipeline at the point of discharge. Another common problem that we come across is that of what we term active and passive cells. This is a situation where the steel is in 2 chemically different situations, one of which does not corrode due to the chemical environment. And the most common situation is that of concrete encasement. Now, this is a river crossing of a fairly significant river, and the pipeline underneath this weir is encased in concrete over its entire distance. At the point where it comes out from the crossing, the pipeline will transverse into soil. So on the one side, we have steel in concrete, on the other side, we have steel in soil, and these are 2 very different electrochemical situations. If they're coupled together, then you will get quite serious corrosion of the section of the pipeline that is in soil immediately adjacent to the concrete. Sometimes this even occurs on a smaller scale during pipeline construction, where valve chambers may be encased in concrete in order to stabilize the large steel pipes. You'll note from this picture that the pipes that go through the concrete are actually coated, and this is one way of ensuring that we can in fact control the effects of this active-passive couple. Pipelines can also suffer from internal corrosion. Although this is not really related to cathodic protection, there are certain situations where internal corrosion can be caused by the other corrosion situations that occur on the pipeline. Most water, or all water pipelines are internally lined, mostly with epoxies. And sometimes if we have sour gas or sour crude, these products also require lined pipes. If that lining fails, then we land up with severe internal corrosion, which can lead to perforation. So now that we know something about these illnesses that affect our pipeline system, we have to diagnose what the illness actually is. We have to investigate what is going on. So firstly, we do physical examination. How many of you have to go for an annual medical every year at the beginning of the year? And what do they do? Stick your tongue out, look in your ears, take your temperature, bash your knees to see if your reflexes work. All these things are regular inspections that are done. So too on a pipeline, we do regular inspections primarily related to the electrical status of the pipeline in order to determine whether or not it is corroding. Sometimes your physician will actually send you off to a specialist, and you may have had a CAT scan or an X-ray or an MRI. So too with pipes, we have a lot of specialized tests that we can do. Here we have a situation where a pipeline is being surveyed in order to determine whether or not there are any problems associated with its installation. These sort of surveys give us results. I don't know if any of you have seen the X-rays. Can you interpret an X-ray? Well, when you get a survey result like this, you often find that people battle to interpret them, and this is where the corrosion specialists come in. So these graphs give us a lot of information about the conditions that exist on the pipeline and enable us to investigate in specific areas where there are problems. We obviously want to establish everything that is wrong by diagnosis. Pathology is the investigation of corrosion that has already happened. So, for example, by looking at the type of corrosion product, we can tell whether the corrosion mechanism was bacterial or stray currents or whatever. This particular example is bacterial corrosion with a highly voluminous corrosion product on the surface. And when we remove it, we find that there's the characteristic shiny surface underneath. And you can see that this particular situation, the pipeline has been perforated by the bacterial corrosion. So pathology is useful, but actually we'd prefer not to have to cut up the pipeline. You don't really want to cut up your patient when you're doing medical stuff, unless, of course, they're already dead. And we don't want dead pipelines. So now, having identified the illness, the doctor looks at what medication is available. Well, the medication that the cathodic protection engineer has is very, very similar to immunization, because actually we use the current that causes corrosion to prevent corrosion. Now that really sounds like black magic, doesn't it? It isn't really. We have a wonderful array of acronyms: SACP, NDUs, ICCP, FDU, and several others. These are systems that can be used to implement cathodic protection. And I'm not going to spoil your appetite by telling you what these are, because we want you to come back in a couple of weeks' time and we'll give you more explanations on what these acronyms actually mean. However, all of them are based on the situation that we use an external current and an external anode in order to convert the pipeline into a cathode and thereby prevent the corrosion reaction from occurring. But to whet your appetite, here's a picture of an SACP system. There is another treatment which is not really cathodic protection. It is like taking a patient and putting them into a sterile isolation ward and closing the door. No entry. This is a passive situation. We are encasing the pipeline in concrete, and the pipeline in concrete is not going to corrode. The problem, of course, is that at the end of the concrete encasement, there is now this active-passive transition. And just as when you open the door to the isolation ward, you let in the germs, so too, if you don't take care, you can land up with corrosion at this active-passive transition. And one of the biggest areas of problems in this situation is reservoirs for water, where the pipeline comes out from being cast in concrete in the reservoir and goes underground. Pump station walls and things like that can also be a problem. So having decided which medication, we need to know how much. I'm sure you've all had a prescription at some stage in your life, which tells you that you have to take 2 capsules 3 times a day with water after meals. Well, the primary prescription that we have in cathodic protection is that of the current requirement. How much current do we actually need to provide from our external anode in order to achieve cathodic protection? And one of the most important contributors to that current demand is the protective coating that is put onto the outside of the pipeline. This coating provides barrier protection. We endeavor to make sure it's defect-free at the time of construction, but all coatings will degrade with time. These coatings provide both mechanical and electrical protection. And this is one of the interesting developments that's come up over the years. As we get better and better coatings, we get better and easier cathodic protection, less cathodic protection current, but we are finding that we get more and more AC interference as the coating insulation values increase. We also need to be careful that the coating selection is combined with the correct laying techniques and backfilling in order to prevent significant damage to the pipelines during construction. Not only do we need to know how much current, but we need to know how far we need to push the patient. Just like we have blood pressure targets in medication, we have cathodic protection targets. And these are set out, for example, in ISO 15589, and they tell us what the various values are that we need to achieve for cathodic protection. And these values change depending on whether we've got standard conditions, if there is such a thing, or bacterial corrosion, or perhaps high temperatures, or very high resistivity soils. All of these things affect which criterion we use. The amount of current that we need is also vastly determined by the level of interference that we have on the pipeline. And this interference comes from rail systems primarily. If you look carefully at this photograph, you may just be able to spot a train in the distance. And this pipeline that we see in the picture is crossing the rail. How much current from that train is going to enter into this rail? We need to find that out for a cathodic protection system to work. Now, some of you have got allergies. I would imagine that there must be some of you out there who are allergic to penicillin. Well, in cathodic protection, we also have allergies. And I think the primary allergy is that of electrical continuity. If a pipeline is not electrically continuous, the cathodic protection system is compromised. And unfortunately, bolted connections are not necessarily electrically continuous, even though they may be indicated as being continuous if you use a digital multimeter. When these sort of connections are put into soil or water, they develop into electrical dry joints. And if you look carefully at those flanges, you can see that each flange has a little welded connection cable across the flanges in order to ensure electrical continuity. If we do not have electrical continuity, then the cathodic protection current will endeavor to jump across that discontinuity. And you can see here some internal corrosion that has occurred at a break in a pipeline. This was obviously a water pipeline. Another allergy that is all too common is that of electrical earthing. Unfortunately, the electrical and safety engineers on a project have absolutely diametrically opposite requirements to cathodic protection. In cathodic protection, we want everything isolated. The safety engineers want everything earthed. And we have to ensure that our systems are correctly designed in order to take care of this. If they are not, as you can see in this photograph in the bottom left-hand corner, there is a supply cable attached to that actuator. And that supply cable, being 380 volts or 400 volts, three-phase, has an earth cable. And that earth cable goes back to the plant earth. If that actuator is not isolated from the pipeline, all the cathodic protection current will be drained into the plant earth system, and the cathodic protection system is compromised. Many medications have side effects. And unfortunately, cathodic protection also has a side effect. When you have a pipeline that is subjected to cathodic protection, any other pipeline in the same vicinity will be affected by the electrical field set up by that cathodic protection system. And here you can see a situation where there are two different pipeline systems. One's blue, one isn't, and they belong to different operators. One of them has cathodic protection on it, one of them doesn't. Here you can see a situation where three different pipelines are being monitored, and the interaction between those pipelines is being tested. This is a subject that is handled by what we call electrolysis commissions. These are commissions which are established in most countries in the world where there are cathodically protected pipelines, and they provide for interaction between pipeline owners in order to ensure that we don't get deleterious interference between parallel or crossing cathodic protection systems in the same area. Well, when all else fails, there's still surgery. And just like the hospital bills that you get when you go in for surgery, the bills for pipeline surgery are extreme. But sometimes it has to be done. And the net result of this, of course, is very costly. And that is why we use cathodic protection, because effectively, if it is done properly, we can avoid surgery. And that is one of the reasons why we can call cathodic protection medical aid for pipelines. Unlike C19 at the moment, although we believe that there are developments happening, there is a proven vaccine against corrosion of buried and submerged pipelines and structures. Please use it. Cathodic protection is similar to using insulin to treat diabetes. You have to continue doing it for it to be effective. If you stop, you'll end up under the knife. So to answer the question that we started with, which was cathodic protection, why bother? The answer is very simple.
I trust that many of you found that that's answered some of your immediate questions about cathodic protection, and perhaps has started you thinking about your own situations and wondering, well, where to from here? Do come again next week and enjoy the rest of your Tuesday. Take care, and we'll chat again soon. Thanks so much.